When talking about various computational models, we already gave a superficial introduction of non-determinism, and now we want to focus on non-deterministic finite automata. Okay, but non-determinism is not just applicable to finite automata. I mean, even for push-down automata and LBA and Turing machine, you can think about determinism and non-determinism. And for all these automatas, what are the common features? That the input is a string, and the string is processed in discrete time steps, right? And at each time step, the automata has some internal configuration, right? So for DFA or even in NFA, that internal configuration is just the state. For other automata, it will be state plus something else, but right now the situation is the most simple thing. So the internal configuration is here the state only for finite automata. Okay, and the deterministic behavior is the next configuration depends completely on the current configuration and the current input symbol that it's seeing. Okay, so what will be the next configuration is uniquely determined by your current configuration. So that is the deterministic behavior. That is true for finite automata, push-down automata, and Turing machine, all those things. So in non-deterministic automata, from a current configuration and on input symbol that you are currently seeing, even if you specify those things, the next configuration is not uniquely determined. It can be this or that. So in fact, the next configuration, you should talk about the set of next configuration, right? Because there are multiple next configurations. So yeah, there is no unique thing. So in case of finite automata, this configuration is state. So for deterministic, we had this transition function, right, which took the current state, current symbol, and gave us the next state. So that won't be the case for non-deterministic finite automata. The current state and the current symbol won't give you a single next state, but a set of next state. So, and we also gave this example in this previous slide, this light switch example. And this non-deterministic behavior looks like the machine is kind of faulty. So if it is on and if you push a switch, then it definitely goes to off state. But if it is in off state and if you push the switch, it may go to on state or it may remain in off state, right? So that we discussed earlier. So this can be modeled by this automata. You have this transition diagram, and you see, if you are in this state, Q off state, and if this input symbol is given, so this next state is not defined if you try to model the transition function as this. So this works for DFA, right? So this works for DFA. This works for DFA. But not NFA, right? So if we want to model this sort of behavior, we cannot take this signature for the transition function. No, this will not work for non-deterministic finite automata. So how can we then model the transition in non-deterministic finite automata? So before going into that, let me just give you a more complex example with all those childish pictures of bulbs and switches. So in DFA you saw that its state and transitions between them on symbols, right? So it looked something similar to this, but now here you see that you have a non-deterministic behavior here, because if you are in Q0 and if you see input symbol 0, then from here either you can go to this state or you can come back to this state, right? So two possibilities are there. So similarly, if you see 1, then either you can remain in this state because of this transition, or you can move to this state because of this transition, right? So there are multiple possibilities, even if you know the current state and the current input symbol. So you start with this state. So this is the starting state. And now suppose you are trying to process this input stream. Okay. So what happens when you see the first 0 here? So you are seeing this input symbol 0. And on this you can move to either Q0 or Q3, right? So the next state is not just a single next state, but a set of next state. Now once you are here, then if you try to process, say, this 1, so now if you followed this path initially, so you are here, so from here you can take you can process 1, right? But if you are here after processing 0, so after processing 0, suppose you took this path and you are here, so from here there is no way to process 1, right? So that means it will get stuck. So there are again multiple possibilities. So in the next step what happens? So this happens. So if you are here, then again on 1 you can either be in Q0 or you can go to Q1. But if you are here after processing this 0, then on this one, from here you get stuck, right? So similarly, you can move to now this input symbol. Again from here you see that there are two possibilities, Q0 and Q3, like this. But if you are in Q1, so from Q1 there is no way to process this 0, right? From here there is no transition on 0. So here you will get stuck, and then the next input symbol is 0. So now you see for both of these states you have some options. If you are in Q0, then you can move to Q0 or Q3. If you are in Q3 here, so then on this 0 you can move to this Q4, right? And finally you have to process this input symbol. So if you do that, it will be like this. Now out of all these possibilities, you see that this is not final. Okay, so this is not final. Sorry. Similarly, this is also not final. So these two are not final, but this is final, right? So in our diagram, this is marked as okay. So yeah. So you see that on a given input string, there is proliferation of path. So you can have many paths which can lead to many different states. So as I was talking before, here if we want to model the transition from a current state, we need to consider the set of next states on a particular input symbol, right? So we can think of some transition function which takes the state, which takes a symbol and spits out not just a single state but a set of states. So the signature will look like this. So it takes a state, takes a symbol, and then what is this? This is the power set of Q. That means the set of all subsets of Q, right? So anything here is a subset of Q. So the value that it gives is some set of states, right? So this is how we can model the transition function of a NFA, right? Though we don't know which one of this will be the next state, but at least we know for sure that the set of next state is just this, okay? That we know for sure from the diagram. So this is a function, right? At least we know what this state will be. I mean, this state is completely determined by Q and A. So this delta is a function. So the automata we mentioned earlier has this transition table, right? So from Q0, if you see 0, then you can move to either 0 or Q3. So that means this delta of, so if I take this and this, so this means the delta of Q0 and 0. So this is this Q0 and Q3. Right? So this is what it means. Now we saw in that example that you can get stuck at some point, and remember in the DFA we also had that behavior when we used partial transition function, right? If the transition function is total, so then you won't get stuck. You can move to dead state and remain there. So we had to distinguish between this total and partial functions, and we proved that if you have a DFA with partial transition function, then you can convert that to a equivalent DFA with total partial functions by introducing something called a dead state or trap state. So if you forgot that, you go back to that video and watch it again. Now here, even if we have this behavior of getting stuck, we do not need a partial transition function. So transition function is always total, okay? So you see, this from Q1 on input 0. So from Q1 on input 0, there is no transition. But now we can say that this Q1, this delta of Q1 and 0 is just phi. So there is no next state, right? So we can use this sort of thing. So this is not an undefined quantity. This is a well-defined set, right? This is a subset of Q. So we do not need to say that delta QA is undefined, but it is empty. So this mitigates the requirement for this undefined transition. So here the transition function is always total. So what is the formal definition of non-deterministic finite automata then? So you have seen this 5 tuple in case of DFA. If you forgot what it is, then again go back. So this is the set of state. So this is a finite non-empty set of states. This is the input symbol, input alphabet. The inputs are going to be strings over this alphabet. You have a transition function, you have a start state, and you have a set of final states. Okay, which is a subset of Q. The only difference is that here the value returned by this transition function is not just a single state but a set of state. That is the only difference. So except for this little part, this entire slide looks exactly same as that of the definition of deterministic finite automata. Okay. Now, what about acceptance of a string? So, in case of DFA, we expressed that as in terms of extended transition function. So, the extended transition function for DFA captured a chain of transition. So, you start from some state Q and you process this string W, and then you end up at P. So we said that P is delta hat of Q and W, something like that. But in case of DFA, this path was unique, right? But in case of NFA, there can be multiple paths. So this proliferation we saw, right? So this is one path, this is one path, this is one path. So there can be multiple paths. Some of them can get stuck also, but even if they do not get stuck, they can reach multiple states. So then how do we define extended transition function, and most importantly, how do we define acceptance of string based on that extended transition function? So like one step transition, this transition function also should be of this signature, right? So now instead of a single symbol here, we are considering strings because we are considering multiple transitions. So yeah, here multiple transitions. So you are given a state here, and then you feed a string, and then you get a bunch of states. What are those bunch of states? The states that can be reached from Q on processing this input string W, right? Now immediately we can define this, because if you are in state Q and if you are processing the empty string, that means you are processing nothing. So you haven't made any transitions. So then you remain in Q. So this comes naturally, right? So now once we have this, how can we fully define this thing? So you remember in case of DFA, it was a recursive definition. Again, we defined it for epsilon, and then we defined it for something like this in terms of say QW, but here the condition will be slightly more complex. So why slightly more complex? Because even if you take this thing, this delta hat of QW, which is supposed to be the set of states which you can reach if you start from Q and process W, so that will be a set of state, right? So you cannot just take this and apply delta over this, okay? So it will be meaningless to apply a delta on this, because delta can only be applied on a single state, right? So if you see what was delta, so delta still operates on a single state. So you cannot take just this and apply delta on that. So what you can do is this. So you have a set of states that you can reach after processing W. So this is this we want to be. We want to define delta hat so that this identifies with this expression. So now, if you process one more symbol, say A. So from here you can reach a bunch of states, right? And what is this bunch of state? This is precisely the delta of P1 and A, right? So by definition of delta, this set of states will be this. Similarly, so here I have shown it as a singleton state. So yeah, the singleton state will be the singleton set of state will be this. And yeah, so for each of this PIs here, you can determine the set of states that it can reach from this PI on processing just this input symbol A. Now if you take the union of all these sets, right? If you take this big union, so this gives you the set of all states that you can reach after processing WA, right? On WA you have all these paths. So starting from Q, if you process WA, you can reach all these states, and these are precisely the states that you can reach. So that means this will be the set of union of all these delta PAs, where this P is coming from this set. Okay, so this is what it is. Now, obviously, in this picture they are shown as different circles, but they need not be distinct, right? All these PIs, Rs and Qs, they need not be distinct. They will not be distinct if you consider long enough path, because you have only some finitely many states, say n many states, and this W can be anything. It can be more than it can be of length more than n. So there will be repetition of paths here, but anyway, nonetheless, this definition holds. So this we can take as a definition of delta hat. So this we can take as the definition of this extended transition function for NFA. And you see that the signature is this. So Q, then a string, and then it gives you a set of states. So if you remember from the video about model of computation, there we actually mentioned the acceptance criteria in a non-formal way. So as we saw, now, so say this is the starting state, okay? I say this is the starting state. And now on processing this W, we can reach multiple states. Here I have shown only 2 states. There can be 1,000 states here. It doesn't matter. Now we say that W is accepted if among these states at least one is final. So at least one will do. Okay. So in this case, this is final, this is non-final. So we say W is accepted. So in this case, both are final. We also say this is accepted. Here, none of them are final, and only then we say that this W is not accepted or it's rejected. Okay. So that means you calculate this thing. You start from Q0. You process W, and then you get a set of states, right? Unlike DFA, you have a set of states here, and if any one of them falls into F, so that means this intersection, if it is non-empty, so then you say that W is accepted. Okay. Now, a common mistake that students often make is like they try to just bring in the idea of DFA into this NFA, and they say that okay, if it takes this path then it is accepted, if it takes this path then it is not accepted. No, acceptance or non-acceptance doesn't depend on a particular path. So there can be many paths. You have to consider all of them before you figure out whether it's accepted or not. So you consider all the paths, okay, all the paths and all the possible states that it can reach after processing the input, starting from the input state of starting state, of course. And considering all those paths, if you see that at least one of the states that it can reach is a final state, so then you say that W, this input string, is accepted. Okay. Make sure that you understand this fully. If you want to pause this video, pause it and just let it soak in. Okay. So again, I'm mentioning that here acceptance and non-acceptance doesn't depend on any one particular path. There can be multiple paths. You have to consider all the paths, and if it is reaching a final state in at least one path, then we say that W is accepted. Okay, this is the acceptance criteria. And what is the language accepted by this NFA? In all automata, the language is the set of all strings that is accepted. So here the acceptance of string is encoded given by this condition. So it's the set of all strings that is accepted. So that is a language, and we say that is a language accepted by automata. Okay. So this is the acceptance criteria for string, and depending on that we define the language accepted by the automata. They're slightly different, right? Now before proceeding further, this is a good time to just ask, why do we even consider non-determinism? See, in the first place, it looks like the machine is faulty, and you cannot say what it is going to do next. It can do this, it can do that. So what's the point of considering such a machine? Computers don't behave like that. It has to do a particular job in a well-defined manner. So that at first looks completely unnecessary and useless, right? And not just that, now the acceptance criteria requires you to consider all the possible paths, right? Now who does that? You run your machine and you do not know what path it will take, and then you have to figure out all the paths and then figure out whether at least one of them leads to the final state or leads to a final state, and then you accept that thing. So that looks completely unrealistic. So you ask how this we have a mathematical model, but how this mathematical model help us to build an actual computer? For DFA it was quite clear. It looked like a proper machine. But here, whatever machine we are describing, it looks kind of an unrealistic thing. Now, this also been mentioned when we talked about model of computation and this hierarchies and all those things, that we have theorems to show that certain models are equivalent to other models. So later we will see that deterministic and non-deterministic finite automatas are equivalent. And what do we mean by they are equivalent? That also I described in detail. So if you forgot, then again go back to those videos. But again I'll mention it. So that means if you can accept a language using a DFA, then you can accept that language using some NFA, and vice versa. If you can accept a language using NFA, then you can also accept that language using some DFA, right? So you may not be able to actually build a NFA as a machine, but at least mathematically, if you can show that you can accept a language using a NFA, so then you know that you can also build a DFA which accepts that language. Okay. So this equivalence makes certain proofs very easy. So we will see in case of finite automata, it helps us, it simplifies the proof that certain language is regular. So what is a regular language? If it is accepted by a DFA, and that will be equivalent to the statement that it is accepted by NFA. So it makes those proofs easier. So instead of trying to prove that the language is accepted by a DFA, it is often easier to prove that the language is accepted by a NFA. So you just do that using the model of NFA, and then since we know by a theorem that it's equivalent to saying that it's also accepted by a DFA, then we are done. And also we will prove some closure properties. If you remember, I also mentioned these closure properties. It's like making new languages using union, intersection, homomorphism, inverse homomorphism, all those operations, and then proving that these newly created languages are also, say, regular or irregular, if it is given that the starting languages were regular or irregular, whatever. So those proofs become very easy if we use this non-deterministic model. Now, this equivalence holds for finite automata, but say for push-down automata, we can prove that the deterministic push-down automata and non-deterministic push-down automatas are not equivalent. In fact, the non-deterministic model is strictly more powerful than the deterministic model. Now, this push-down automata, so these are actually used in solving real-life problem. For example, you know about compilers. You write programs in C or C++ or whatever language, and then you compile it, right? So the syntax of this language is designed according to this context-free grammar, which is equivalent to this push-down automata, right? So this compiler then acts as a push-down automata which can accept your program, and it also produces the compiled output, right? So the compiler that you are writing is actually a push-down automata. And since here you know that the deterministic version is strictly weaker than the non-deterministic version, so you try to make sure that the syntax of your language is such that it can be processed by a deterministic deterministic push-down automata, right? So if you design a programming language which cannot be recognized by deterministic PDA, and you have to write a program which kind of now try to emulate the behavior of a non-deterministic PDA, so then it will be very inefficient, right? So it helps us to avoid this bad syntax, this bad design. So in both cases, we have advantage of studying this non-deterministic model. So either you study it and show that it's equivalent, so that makes life easier in certain ways, or you study those non-deterministic model and prove that this deterministic model is not as powerful. So then while trying to design your system using those kind of automata, you try to avoid the designs which requires the non-deterministic automata. Okay, so in both cases this study of non-determinism helps. And in certain cases, actually, we do not know whether the deterministic version is equivalent to non-deterministic problem or not. For example, this linear bounded automata, we do not know. So for normal Turing machine, we know that determinism and non-determinism are equivalent. But for polynomial time Turing machine, we do not know whether this deterministic and non-deterministic polynomial time Turing machines are equivalent or not. And this is the famous P versus NP problem. Okay, so this sort of questions are very hard to answer, and they're very fundamental and very deep questions in mathematics, right? So if you solve this problem, you will win the Millennium Prize, right? So your name will go into history. So these problems are that important. So in any way, whether we can prove this and show that it is equivalent, or we can prove this and show that it's equivalent, or if we do not know this and are trying to prove this, in all sorts of ways, non-determinism is helpful and interesting and important. So anyway, so that was a argument in favor of non-determinism, in favor of studying non-determinism. And as you go along, as you actually see how this non-deterministic finite automata, non-deterministic PDA, non-deterministic TMs are working, things will be clearer to you. So right now it's just some high-level talk. So the actual mathematics and actual details will be clear as we go through all those chapters, but that will take time, and it will take the entire course. So we mentioned that certain languages are easier to be recognized by a non-deterministic PDA. So we in fact solved this problem for DFA, right? We designed a DFA for this problem, and we saw that the design required some non-trivial thinking. So it's not that it's just immediate and you can do it in seconds, right? So we have to kind of think, okay, what the states mean. Maybe one state means that it has 0, 0 at the end. One state means it has 0 at the end but not 0, 0. Another state means it neither has 0 nor has 0, 0 at the end. And considering those states, we put the transitions. So there was some non-trivial approach to solve that problem. And after that, we had this automata, right? So it doesn't look too simple. And then if we slightly modify this problem, so it ends with either 0, 0 or 0, 1, you see that it again gets considerably complicated, right? We have one more state and we have 3 more transitions, and you have to sit down and figure it out. I mean, you cannot just do it immediately in your head. Now, these problems are naturally kind of calling for a non-deterministic model. So now if you see some non-deterministic models which accept this language, you will see what I mean. So instead of all this things, all this DFA, we can have this NFS, right? So what is this language? The set of all strings that ends with 0, 0, right? So how do we think about this sort of string? So that means it has something, some 0, 1, 0, 1, 0, 0, 0, 1, 1, 0, 0, 1, 0, whatever is going on, and at some point in time, it says 0, 0, and then it stops, right? So that is what it is, right? Now look at this NFA, what it is doing. So it can loop in this state for some time, right? here. So it can loop here accepting some combination of zeros and ones, because it can take this thing on 0 and 1. So it can take anything 0 0 1 0 1 1 0 0 1 0 1 0 whatever, and then at some point in time it takes this path, so it leaves this thing 0 0 and ends, right? So it is as simple as that. So whenever you see this thing, you in your head can immediately see this NFA, right? Unlike the DFA. And then all these problems, they are just variants of this thing. So here we have 0 0 as substring. So that means, okay, you have this thing, you take this arbitrary combination of 0 1, then you take this 0 0, and then again you take some arbitrary combination of 0 1, right? What is this thing? So you first process a arbitrary combination of 0 1, then take this 0 and then take either 0 or 1, right? So it ends with either 0 0 or 0 1. So all these problems, they just look kind of the same problem with just minor variations. But here, the difference from here to here is considerable, right? And you cannot do it without pen and paper, at least when you are doing it for the first time. But here, it's immediate. The way we think about this language is in terms of non-determinism. So we are already doing this non-deterministic kind of behavior in our head when we are trying to see what this language is. So in that way, non-deterministic finite automatas are useful. They kind of naturally express certain things. Okay, so it's obvious that non-deterministic finite automatas are generalization of DFA, right? So you can take a non-deterministic automata. So in non-deterministic finite automata, you are allowed to have this sort of transitions, right? You are allowed to have this, but there can be just one transition here, right? So that is also by definition a NFA, a special kind of NFA which has one transition instead of more than one transition, right? And that will be a DFA, right? So it's completely clear that NFA is a generalization of DFA and DFA is a special case of NFA. The only difference is that here we have changed the signature. So instead of Q, here we have said it's some subset of Q. So you cannot just say that this thing goes to just a single state. You can draw the transition diagram like this, but then when writing down the equations, you have to consider this as a singleton set. So so you have to consider this thing as a singleton set, right? So you have to consider this as a singleton set. This thing, if you have a single transition, okay. So this is what this proof is. This is obvious. You do not require a proof here, but I have written this proof because you need to get familiar with the formal way of writing down these proofs, right? And you will see that almost always we will use induction, right? So what we are doing, so we are trying to prove that given a DFA D, we can have a equivalent NFA N, right? So this is given, this we want to construct so that they are equivalent. And what do we mean by they are equivalent? That means they accept the same language, right? And what was the acceptance criteria for this deterministic finite automata? So it was something like this. So you take the extended transition function for this. So here we have this delta D. So you take the extended transition function for this, and you see what the state is after processing W. And if it is a final state, if it is an element of F is the set of final state, so then W is accepted, right? On the other hand, what was the acceptance criteria for this thing? So again, if you take the extended transition function, but for transition function of NFA, right? So that means this is a set of state, and if any one of them falls into F, so that means if this intersection is non-empty, so then W is accepted. So all you want to prove is that this happens if and only if this happens. So then you have proved that this is in this language, if and only if this is in this language, so that means they are equal, right? And for this, how do you design this DFA? So it's the same state, same alphabet, same starting state, same final state. But just we write the transition function as this. So earlier we had the next state as just this delta D QA. So now we write this as a singleton set, and this is what this delta n of QA is, right? So with this definition we try to prove this thing. But instead of proving it just for Q0 and just for this F and F here, it's better to prove this, that this transition functions are essentially same. So whatever you have here with any state Q and any state any string W, you have the same thing here with that state and that input string. But the only difference is that here the result is a singleton's set containing the set which is the set here, right? And then the induction is on the length of input string. So base case is length 0, so that means this is the empty string epsilon. So by definition of this Q hat for both non-deterministic and for deterministic, so this will be the set containing the empty string. This will be the singleton set containing Q, and this is the set Q itself. So if you see the definition of Q hat for DFA, so if you forgot that, go back to the DFA video. So by definition this holds, and the base case for empty string is done. So then you do this induction step where you express this as a string and a symbol. So this string is of lesser length, so the induction hypothesis holds. So that means this holds by induction hypothesis, and using this you prove that this is actually equal to this, right? So this is just formally applying all the equations that we derived, okay? And if I ask you to write a formal proof, so this is what you should write, this kind of thing that you should write. But we actually see the solution in terms of pictures, in terms of those paths and all those things. So it's just a matter of translating those pictures in terms of equations. And as I mentioned repeatedly, the tool that we use is almost always induction on input string length or something else. Okay, so so that means this shows that for any DFA there is an equivalent NFA. Proof is trivial. The fact itself is trivial. What is not so trivial is that given any NFA, there is an equivalent DFA. Why it is not so trivial? Because NFAs seem to be more powerful, right? They have all the power of DFA, and then on top of that they can have multiple transitions, right? But we are saying that okay, in spite of having this apparently more power or more ways to handle things, we can show that if you have a NFA, then you can construct a DFA which accepts the same language as that of the NFA. So that will be the topic of the next lecture, and together with this result we can conclude that NFAs and DFAs are equivalent.